Greetings to the viewers of the channel. All of you are probably well acquainted with such modules. This DC-DC boost converter is frequently used by radio enthusiasts and is implemented in a variety of DIY projects. And today, I intend to thoroughly check all its parameters. You can find a link to such a converter in the description. There, by following the first link, you can read a very detailed article about this converter. And now, let's get started. The parameters claimed by the manufacturer are now visible on your screens. The schematic looks as follows. I won't explain how it works, as this channel is of a slightly different format, but on my main channel, there are plenty of videos with DIY converters of this type. Let's start with the simplest thing, shall we? Let's assess the quality of the assembly and the board under a microscope. The heart of this converter is the MT3608 chip. It combines a generator and a power transistor in one, so there are only a few components on the board. As we can see, the boards are of quite good quality. The assembly is also up to standard. Checkmark, test passed. Second test. Output voltage. The manufacturer claims 28 volts. Let's see if the module will deliver this voltage with an input of just a few volts. This is the voltage of a single lithium-ion battery cell. By the way, I forgot that the inverter won't start just like that. At the very beginning, there's a multi-turn trimmer resistor. You need to turn it 10 steps counterclockwise. And only after that will the inverter start boosting the voltage. As we can see, here too, almost everything is fine. By the way, the maximum output voltage can reach up to 40 volts. To achieve this, you need to short the specified 2 leads on the trimmer resistor, which I strongly advise against doing. One of the test boards burned out at an output voltage of 40 volts and a current of only 100 milliamperes right during the test. It's a pity the camera wasn't on. The minimum input voltage is about 2 volts. That is, the circuit will start working if the input voltage is not lower than 2 volts. And, as we can see, the board remains operational at an input voltage of V. I also came across units that worked from V. The maximum input voltage is 24 V. You cannot supply more to the board. Let's check if this board can handle 24 V at the input. As we can see, everything is fine here too. I set the maximum possible voltage at the output. The no-load current is negligible, only 6 milliamperes, which is very good. And now it's time to put this little guy under load. Let me remind you, the manufacturer claims a peak output current of 2A. To benefit the manufacturer, I will make the minimum difference between the input and output voltage. We supply 12 volts at the input and set 14 at the output. If the module does not deliver the claimed 2 amperes under such conditions, then, with a large difference between the input and output voltage, it will not be able to deliver the specified current. On the electronic load indicator, we see the output voltage, and on the power supply, the input voltage. And now we slowly increase the current. With an output load of 2, and the voltage at the output of the boost converter significantly dropped, therefore, the module is not capable of delivering 2 amperes of output current. The maximum current at which the output voltage remains stable is about. So, this parameter does not match the claimed specification. Let's leave the inverter under load for about a minute and check the heat dissipation on the chip, diode, and inductor. The worst part is that the inductor had to be replaced because it started to smell like varnish after a minute under maximum load. As we can see, the new inductor heats up to a temperature of 60 degrees, but the diode is the most stressed. The temperature is off the charts, and after a minute of operation, it exceeds 100 degrees and continues to rise. The heat dissipation on the chip itself is also enormous. The temperature is around 100 degrees. On the output voltage waveform, ripples are visible. They can be eliminated by adding an electrolytic capacitor rated at 35 to 50 volts and with a capacitance of 47 to 220 microfarads to the output. The generator operates at a frequency of about 1 MHz. Now, let's imagine a scenario where you accidentally reversed the polarity of the connection. Will the board withstand such a fairly common occurrence? The board burned out completely and, even when connected correctly, shows no signs of life. Moreover, it was specifically the chip that burned out. Now let's create a short circuit at the output. And, as we can see, the circuit draws 5A. If the lab power supply didn't have a current limit, the board would have burned out. Therefore, be extremely careful when powering from batteries. In conclusion, I want to say that during the tests, 4 boards were damaged. The first one burned out from overload, the second couldn't handle 24 volts at the input, the third sample burned out from reverse polarity, and the fourth board burned out when I tried to get the maximum output voltage by shorting the leads of the variable resistor. Friends, I also wrote a detailed article with the tests, and right now, by clicking on the annotation, you can check it out. The link will also be in the description. Well, friends, is our test completed? Draw your own conclusions. Just check the link to the converter, as I already mentioned, you'll find it in the description. Don't forget to share the video, subscribe to the channel, and give it a thumbs up. Because that's how you support the life of this channel, and of course, write in the comments about the products you want to test, and I'll do it for you. That's all for now. See you next time. Bye.